This video is just going to serve for you to take your notes on Lenz's law. We will actually do some demonstrations and practice in class because this one's a challenging one. This one is not readily apparent to pretty much a lot of people who study physics, and yeah, it's kind of tough. So anyways, Lenz's law is stated there for you in your notes. All right, and what it tells us is that it tells us what the direction of the induced EMF will be. Okay. It says that an induced EMF, the direction of an induced EMF is such that it produces a magnetic field whose flux opposes the flux change that induced it. In other words, that EMF, all right, will be induced so as to keep the net flux constant. Okay, what that means is that the negative sign that's there in Faraday's law tells us that the flux that is being made, okay, is opposite to the direction of the flux being generated by the EMF itself. All right. So in other words, if you look at that first image there, no, actually I'll write that definition. Okay, an EMF will be induced so as to keep the net flux constant. The original flux change, okay, if we're moving our magnetic field through these wires, all right, is going to cause an increase in magnetic flux lines going to the right. All right? So what we want to see is that the induced EMF, the induced current, is going to produce a flux that's going to be increasing, or producing field lines going to the left. Okay? If we use our right-hand rule, remember our right-hand rule for a magnetic field and loop of wire is if you put your thumb in the direction of the current, okay, your fingers point into the loop in the direction of the magnetic field lines. So what happens here is that if we have the case here in this first drawing, or where we have the magnetic field increasing, in other words, the magnetic field lines are increasing towards the right, okay, the direction of them, that we will generate the magnetic field, or the induced current, will generate a magnetic field towards the left to oppose this. Now this has to do with conservation of energy, which we will talk about in class a bit more, all right? But what we see is that in order to produce those magnetic field lines to the left, our current must be going around in the direction that you see on your paper there, okay? So the result is that the net flux through the loop is held constant, okay? And the thumb points in the direction of the current that is made, okay? We see that we have positive here on this end and negative here on this end. Remember, we're always showing the direction of conventional current, all right? And the conventional current comes out of the positive end. Remember, this loop is like a battery. Okay, think of this loop like a battery. So what we end up having here is a battery between these 2 points, all right? And then we have the rest of the circuit. Okay. So we can also have the same thing. If we move the magnetic field, all right, out of the loop, we're actually decreasing the flux. In other words, what's happening, all right, is that the magnetic field lines that are pointed towards the right are decreasing. Okay. Since we have a decreasing flux from the right here, all right, we need to increase the flux in that direction from the current in the loop, right? Which means that the induced current is going to go in the opposite direction, which you can figure out with your right-hand rule. Just come up here, look at the right hand in that image, and use that down here. Okay. You see that induced current goes around in that direction, and now what we've done, okay, is we've switched the polarity of the circuit, okay, or the direction of the current in the circuit, is what I mean, okay, the direction of the positive and negative, all right, ends of our loop. Okay, let's do this a bit more. So we have a couple of diagrams here showing a conducting ring that is placed in a uniform magnetic field that is changing at a constant rate. Deduce the nature and direction of the induced current in each situation. So the first image here, we have a magnetic flux that is increasing, whether it be, see here, it looks like since we have the conducting ring, the ring stays constant. It's just going to tell us that the strength of the magnetic field was probably increasing, okay? So we have the strength of the magnetic field constantly increasing, all right? If we look at our equation here, remember our EMF, which is equal to negative N times delta Q, all right, from delta phi, my goodness, not enough coffee, all over delta T, all right? Remember that current is just EMF divided by R, so it's just divided by some resistance. So this positive slope here means we'll have a negative EMF, we'll have a negative current, right there. All right, so the next one here, when we draw this graph, we have a decreasing flux, okay, which tells us that we're going to have a positive EMF, a positive current. There we go. That's what it's going to tell us, okay? So if we actually want to know the direction here, we just have to use our right-hand rule, all right? So the increasing flux, the flux is increasing into the board. That means the EMF, all right, is going to have to be increasing out of the board. So we want to have our fingers pointing out of the board with a right-hand rule for a coil of wire, all right, which means that if we use that, the thumb points in this direction, all right? So we go in like this, okay? Using the same logic, since it's going to be decreasing into the board, we need to have it increasing into the board. And if we show our thumb in that direction, it goes around this way. So this is clockwise, all right, this one is counterclockwise. Try a few more examples here, all right? You just have to constantly do examples with Lenz's law. And just imagining the magnetic field growing in strength and decreasing in strength, all right? Another magnetic field, remember magnetic field lines go from north to south outside the magnet here, so if we push the magnet this way, and all these field lines are pointing this way, the magnetic field is going to be increasing in strength throughout the solenoid. All right, so we need to have the flux from the induced current. All right, the induced current here must produce a flux to the left. Okay, so it produces a flux to the left. So in order for that to happen, all right, we see that the current needs to go this way and come around this way, all right? So we see the current is going that way. Here, there's no current. And here, the current would have to be in the opposite direction, all right? Because it would have to produce an increasing flux towards the right. If you don't remember that, go back to your notes last year on the magnetic field produced from a solenoid. A few more examples here, all right? This is another right-hand rule. Remember, if we have a current going through a wire, it produces a magnetic field. And if you put your thumb in the direction of that current, the magnetic field, right, comes around like this, okay, into the board there, out of the board up here at the top. And actually, if I draw that, I can draw that a bit better for you to see here. All right, so into the board here below. And out of the board. Excuse me. I have drawn that oppositely. There we go. Okay, let's switch that. Sorry. Into the board, little X's. There we go. Out of the board, like this. There we go. Okay. So if the current, all right, induced current is, if the current in the wire going across here is increased, it's going to increase the magnetic field flux going through our little rectangular loop of wire. So if that's the case, we need to increase the flux coming out of that loop of wire to counteract that from the induced current, okay? And in order to generate that kind of a magnetic flux using your right-hand rule again, you're going to need a current going in this direction. Same thing over here, except that now it's decreasing, the current's decreasing the magnetic field through the rectangular loop. That strength, that flux, all right, will also be decreasing, so you need to increase the magnetic flux into the board, and that's going to require current going this way, all right? Again, we're going to go over these examples in class, but there's multiple steps here, I suppose, that you want to be paying attention to. All right, so the first thing whenever you're trying to determine the direction of an induced current, okay, is which way does the external magnetic flux change? First question you must answer. Second question you must answer, or point to make, okay, is that the induced current will produce a flux in the opposite direction. Okay? Determine the direction of this current from your right-hand rules for coils of wire, solenoids, all that business. All right, those are the 3 steps that I'm using. All right, final point here to make. A conducting loop, the final question to answer here, sorry. You got a conducting loop of wire moving at a constant speed into and through a uniform magnetic field, okay? So what we want to do is indicate the direction of the induced current as well as the flux through the loop. And also the, what the induced EMF is during those times, okay? So the flux through the loop, as we go through here, there's no flux through the loop in the first part. In the second part, right, the flux is increasing until it gets to the point where it's no longer changing, but it's a constant amount, all right? Then it decreases to 0, and then we've got 0 over here, okay? So it should look something like that. When the loop first enters, okay, it's an increasing flux into the board, so we want an increasing flux out of the board. In order to get that, we need a current that's going to go in this direction. This guy over here would be the opposite direction, okay? What we have here, right, to get the direction of that induced current, you could use that, or you could use the right-hand rule, like we used at the very, very beginning, all right, of the chapter. The EMF induced, remember, is only going to be caused when we have a changing flux. With a positive changing flux, okay, well, the first part, first of all, 0. The positive changing flux is constant, right? It's a constant slope there, so it would be negative EMF induced there, back to 0, across the middle, no change in the flux. And up here, we have a negative change in flux, so it's a positive EMF induced, and there we go, that is it. That is what your EMF curve will look like, a little square waveform, okay? So that's it. That is Lenz's law, and we'll do more practice and simulations with that in class.